This is Lab 5, Rotational Kinetic Energy of Rolling Objects, in Physics 2211, Samantha Hefner. So what I chose as the purpose of this lab is to investigate how the shape of an object affects its motion. More specifically, how the different moments of inertia affects the velocity of an object rolling down a ramp. The fundamental physical principles used are the work energy theorem, and then translational and rotational kinetic energy. Results. The final velocity of an object rolling down a ramp is due to work done by gravity, but it also changes depending on the shape of the object. So for the work energy theorem, it states that work is equal to the change in kinetic energy plus change in heat energy. For this experiment, we can assume there is no heat lost to the surroundings. So the work, which is going to be the work done by gravity, is equal to the change in kinetic energy. But there is translational and rotational kinetic energy of a rolling object. So the work done by gravity is going to be equal to the change in translational kinetic energy plus the change in rotational kinetic energy. The equations for each are shown here. The translational kinetic energy is the change is equal to 1/2 mass velocity final squared minus 1/2 mass initial velocity squared. For rotational kinetic energy, it's similar, but it's 1/2 I, which is the moment of inertia of the object, omega, which is rotational velocity, final squared, minus 1/2 I omega initial squared. But we can replace omega with velocity divided by radius. So the change in rotational kinetic energy we can rewrite as 1/2 I final velocity over r squared minus 1/2 I initial velocity over r squared. So here are the moments of inertia of the two objects I tested. I did a cylindrical hoop with a moment of inertia of mass times radius squared and a solid sphere about a diameter, which has a moment of inertia of 2/5 mass times radius squared. So I did some calculations. The work done by gravity is equal to the change in translational plus the change in rotational kinetic energy. The work done by gravity can be rewritten as mass times gravity times delta y, which is change in height, and that's going to equal 1/2 mass times velocity final squared minus 1/2 mass initial velocity squared for translational plus 1/2 I omega final squared minus 1/2 I initial omega squared, which is the rotational. Because it's starting from rest, we can take out both of the ones with initial velocity, and so mg delta y is equal to 1/2 mass final velocity squared plus 1/2 moment of inertia angular velocity final squared. Mg delta y equals 1/2 mass final velocity squared plus 1/2 I final velocity over r squared. Okay, so then we use this to find the final velocity of both the solid sphere and the cylinder. So you just have to plug in the different moments of inertia for each object. When we end up working the calculations, the mass and also the radii of both objects are going to end up canceling out, showing that the three factors that determine the final velocity are gravity, the change in height, and the factor of the moment of inertia, or the coefficient for the moment of inertia in front of the mr squared. So for the ball, it's the square root of 10 over 7 gravity delta y, and for the cylinder, it's just the square root of gravity delta y, indicating that the solid sphere should have a greater final velocity than the cylinder. So I tested it, and here are the videos. Here is the cylinder, and here is the ball. When tracked with tracker, we can see in the position versus time graph of each that the ball took 0.5 seconds to roll down the ramp, and at the same height, the cylinder took 0.7, about 0.7 seconds to get down the ramp. So this indicates that the ball did in fact have a greater final velocity than the cylinder, which matches with the theoretical results calculated before. Thank you.